So as I said before at the start of this chapter, there are two types of electrochemical processes that we're going to look at. The first type is where a chemical reaction produces an electric current or energy in the form of an electric current. And then the second type of process is where an electric current is used to drive a non-spontaneous reaction. So we're going to deal with the former first. And what you're looking at here on your screen is what is known as a galvanic cell. So let me just get into a description of what this is all about and show you how it works. So on this side here, we have a solution of zinc sulfate and we have a metal zinc, which is dipped into that solution. All right. That zinc is connected through an electrical wires to the other metal here, which is copper, which itself is dipped in a solution of copper 2 sulfate. All right. We have this instrument here, which is known as a voltmeter. The voltmeter measures what we call the cell potential. All right. And the cell potential, simply put, is basically a measure of the tendency of the electrons to flow from one cell to the other. So as you can see here, electrons are flowing through the external wires right here. All right. So what is happening here is that when the zinc is dipped in a solution, you're going to have a reaction taking place where the zinc metal is converted to the zinc ions, all right? And that is basically shown in this diagram right here. So basically, the zinc will be oxidized. If you go back to the definition that we talked about in terms of oxidation, oxidation involves the loss of electrons, and that's exactly what's happening here and described in this equation right here. Zinc is undergoing oxidation by the loss of 2 electrons to form the zinc ions. So those 2 electrons that are lost will actually enter the external circuit, all right? So that's what happens over here in this particular, what we call half cell, right? As the electrons flow through the external circuit, it's going to come through the copper here. And what's going to happen in this solution right here is that the electrons will basically combine with the copper to form copper metal, right? So basically what will happen is that the amount of copper will increase over here because copper metal is being formed. That is shown in this diagram right here, where the copper 2 plus is gaining the 2 electrons to form the copper, which will be deposited on the copper electrode right here. And this is the half equation that represents that particular reaction. So as you can see here, reduction is taking place in this half cell because the copper 2 plus is gaining 2 electrons to form copper metal, right? So basically, this is a redox reaction overall that is taking place here, where the zinc is being oxidized to form the zinc 2 plus, and the copper 2 plus is being reduced to form the copper solid, right? So, as is the case in any typical redox reaction, if you have oxidation taking place, then reduction must be taking place. And also, the number of electrons lost and gained will be the same, all right? So that's basically what happens in a typical galvanic cell. So it is this reaction here, the net equation here, which is providing the energy which produces the electric current that flows through the external circuit, right? So this is a spontaneous redox reaction. Again, the term spontaneous basically means that the reaction will take place by itself without any energy source making the reaction occur, all right? Now, I want to spend some time, before we get to the salt bridge, some other definitions here. So basically, the zinc electrode, or all of this here, is called the anode. And the anode is where oxidation takes place, right? So basically, the electrode where oxidation takes place, the electrode where electrons are being lost, that is called the anode. While the cathode is where reduction takes place, all right? So that is true for the galvanic cells, and that's also going to be true later on when we're discussing electrolysis, but that's later on, all right? Now, I want to spend some time talking about the role of this here, which is called the salt bridge. The salt bridge is usually some inert material, usually agar gel, which is soaked in a particular ionic solution. In this particular case, it's a solution of potassium chloride. Now, the role of the salt bridge in this particular setup is very important because if you allow this to occur without the salt bridge, let's say you set this up, but you do not add the salt bridge, then what's going to happen is that in this half cell, the amount of zinc will increase to a very high amount, relatively speaking, and over in this half cell, the amount of copper 2 plus will be reduced. The result of that is that eventually the electric current will stop flowing, all right? Because basically, as a result of the relatively high concentration of the zinc ion present, that would basically reduce the amount of electrons that will be lost and therefore enter the external circuit, all right? So the role of the salt bridge is basically described here. For the cathode, as I said before, there'll be a buildup of the zinc ions. So what will happen in order to maintain electrical neutrality in the cathode is that the zinc ions will move into the salt bridge, and at the same time, you're going to have the chloride ions from the salt bridge moving into the solution. And then for the anode, what's going to happen is that because of the reduction of copper 2 plus leading to a depletion of the copper 2 plus ion, and therefore what you're going to have is an excess of sulfate ions. So what will happen in the anode is that the sulfate ions will move into the salt bridge, and at the same time, you're going to have potassium ions moving from the salt bridge into the solution. So that's basically what the role of the salt bridge is to maintain the electrical neutrality of each half cell, without which what will happen is that the current will come to a premature end as a result. All right, so that's the important role of the salt bridge in this setup. So we can measure, as I said before, what is called the potential, cell potential. In fact, there are different terms, which basically means the same thing. You can call it cell voltage, the electromotive force, which is a bit of a misnomer because there's no actual force that is involved. But, you know, this term is a holdover from ancient times when not much was understood about the nature of electric currents. And then we have the cell potential, which is probably the most common term that is used to describe the measurement of the potential between the two half cells, right? So this is basically showing you an instrument known as a voltmeter. Basically, you connect the electrodes to the voltmeter and you get a digital readout of the potential between the two cells. We can use a shorthand representation of a typical galvanic cell by using what is called a cell diagram. So this would be the redox equation for the cell that we looked at earlier in the previous slide. And the cell diagram is going to look something like this. Now, we're assuming here that the concentrations of all the ions would be 1 molar. So the copper 2 plus concentration and the zinc 2 plus concentration are both 1 molar. So the way we start off writing the cell diagram, which is a shorthand way of representing the composition of the cell, is that on the right side, or I should say on the left side, we're going to write down the composition of the anode, all right, where the oxidation takes place. And we start off with the substance to be oxidized, which in this case would be the zinc, and then we draw a line, and then we write down the formula for the oxidation product, which would be the zinc 2 plus. And we also include the molarity, which is 1 molar, right? We should also include state symbols. Since zinc is a solid, we put the state symbol for zinc right here. Then we draw 2 lines. The 2 lines here, 2 vertical lines, basically represent a separation between the 2 half cells, just to make a distinction between the 2 of them. And then the next half of this representation, the cell diagram, is where we write down the composition of the electrode, or I should say the cathode, where we start off with the substance to be reduced, which in this case would be the copper 2 plus. Its molarity is given here. Then we draw a line and then we write down the reduction product. So this is basically how we write down the cell diagram for a particular galvanic cell. In this case, the cell which is made up of zinc electrode on one half, or in one electrode, and the other electrode would be the copper electrode. All right. Okay, let me talk about what we call the standard reduction potential, because the key thing you need to remember when it comes to measurement of potential, going back to this here, or going back to even this diagram, the first diagram I showed you, when you're measuring the potential between 2 half cells, basically the potential is a measurement of the potential of one half cell in relation to the other half cell. And therefore, as such, one cannot determine directly the absolute potential, because in order for you to get any measurement of potential, it's a matter of linking 2 half cells together. You cannot basically get the potential of one half cell. So that is a bit of a problem because, we need to make meaningful comparisons sometimes between different half cells. So what was decided by the powers that be is that we define one particular special half cell as having the potential of 0. So that is set at 0. And then any other half cell that is hooked up to that particular half cell, whatever the resulting potential difference is, that would be the absolute or regarded as the absolute potential value. So the special half cell is known as the standard hydrogen electrode, which is this right here, this setup right here. And it is made up of a solution containing 1 molar hydrogen ions. In this case, the hydrogen ions are provided by the hydrochloric acid here. You have a platinum electrode, which is an inert metal, which allows for the electrons to enter into the solution or out of the solution. And we have hydrogen gas here, which is allowed to flow through here at a pressure of 1 atmosphere, all right? So basically, this is called the standard hydrogen electrode, She, and basically that is assumed to have the reduction potential or the voltage set at 0, all right? Now you'll notice here, we call this here the standard reduction potential, E0, 0 being a subscript, or I should say a superscript right here. This 0 here basically indicates that the conditions are standard conditions. And this is something that this symbol here is something you should have met before in General Chemistry 1 when you were discussing thermochemistry and more specifically standard enthalpy, right? And if you remember the standard conditions that little 0 represent would be that, let me get to my writing thing here, would be that the temperature, let me do it here, where's that thing? Okay, so the temperature, the standard temperature is 25 degrees Celsius, and the standard pressure is 1 atmosphere, which is what we have down here. And any solutions, the molarity would be 1 molar, and I think that's it, right? So those are the standard conditions. So if all these conditions are met and you measure the voltage, and that would be the standard voltage or the standard electrode potential, all right? So let me go back to my pointer here. So the reaction that we're talking about here, which would be the reduction reaction, would be shown right here. H plus electrons to give you H2, and this is the balanced half equation for this particular setup, the standard hydrogen electrode, right? So as I said before, that is assumed, the standard reduction potential for this half reaction is assumed to be 0. And therefore, basically, we can hook up other half cells to this setup, and whatever the voltage that we get from that would be in relation to 0, which would be the value that we will accept as a reduction potential for that particular half cell. So, for example, let's look at this setup here where we have the standard hydrogen electrode and it is connected to the zinc electrode that we talked about earlier, right? The conditions are standard conditions, including the fact that the molarities are 1 molar in each case. Hydrogen gas is 1 atmosphere, and I'm assuming that the temperature is 25 degrees Celsius, and so on and so forth. So basically what we find is that we have electrons, when this is set up, we have the electrons flowing from the zinc to the standard hydrogen electrode. And this here would be, of course, the cell diagram for this particular setup. So obviously the anode reaction is where the zinc is oxidized, as you can see from this half equation here. And the reduction reaction would be where we have the hydrogen ion undergoing reduction to form hydrogen gas, right? So the net equation for the reaction is shown here when you add these two together and the electrons are canceled out, all right? Now, it was determined that the standard EMF of this particular setup is 0.76 volts, all right? So the standard EMF of the zinc sulfate is said to be 0.76 volts because the EMF of the cell would be the difference between the standard EMF of the cathode minus the standard EMF of the anode. So that's basically how we calculate the EMF of the combination of these two cells right here. Now, we know that the EMF of the cell is 0.76. That was measured. So that would go here. The EMF of the anode, which would be the zinc electrode, we don't know, but we know that the hydrogen half cell would be 0. So therefore, 0.76 volts, which would be the EMF of the cell, would be equal to 0 minus the EMF of the zinc half cell. So that tells us that the EMF of the zinc half cell is minus 0.76, right? So that would be the standard EMF of the zinc half cell, all right, in relation to the hydrogen half cell. And that, therefore, would be a given value for the standard half cell for zinc, right? So what that means is that for the reduction of zinc, right, in this setup to form zinc metal, this would be the standard EMF value, all right? So that's what happens when you connect the standard hydrogen electrode to the standard zinc electrode. Now let's look at what happens in a case where the standard hydrogen electrode is hooked up to the standard copper electrode. So this is, of course, the diagram for that. And in this particular case, what was found is that the electrons will be traveling from the standard hydrogen electrode to the zinc electrode. So therefore, it is the hydrogen standard electrode where oxidation was going to take place. And the equation for that reaction would be the reverse of the reduction reaction that we saw earlier. In other words, this equation right here. While in the case of the copper half reaction, which occurs in the cathode, where reduction is going to take place, this is the half equation for that reaction. So when you add these two equations together, what do you get? The two electrons canceling out here, and this would be the net equation for this particular setup. So let's see if we can calculate the standard electrode potential for the copper. This is the standard EMF of the cell itself. So again, we're going to use the same equation right here. The EMF of the cell will be equal to the standard EMF of the cathode minus that of the anode. So the cell EMF would go here. The hydrogen electrode, which would be the anode, that would be 0 here. So this is basically the setup right here. And therefore, we can say that the standard EMF of the copper half cell would be equal to 0.34 volts relative to the hydrogen half cell, right? So this would be accepted now as the standard EMF of the copper electrode, right? So that's basically how you determine the standard EMF of different electrodes. We basically compare them, or connect them, I should say, to the standard hydrogen electrode, and then we take the measurement, and then based on that, we can determine the EMF value for these half cell systems, all right? And basically, you can do this with several other half cells, and there are tables that have been generated. In fact, there's one table which is provided for you in Canvas, which gives you these values here. Now, this table here is a much smaller table in terms of the number of different half cells and their half reactions. So the one that you'll have access to is more comprehensive, all right? And these are called standard reduction potentials. And please note that each of these half reactions in this table, and also in the table that is provided to you, are reduction half reactions. So these values here gives you the reduction potential for these reduction reactions right here, these reduction half reactions, all right? So some points about the standard reduction potential, or the standard EMF. It is for the reaction as written. The more positive the standard reduction potential, the greater the tendency for the substance to be reduced, right? So basically, for example, the highest value here is where the standard reduction potential is 2.87. That's for this reaction here. So basically, there's a high probability compared to the standard hydrogen electrode. There's a high probability that the fluorine here will gain 2 electrons to form the fluoride ion, all right, for example. Okay, another thing too you need to recognize is that half cell reactions are reversible. When that's the case, the sign will change, right? So if I were to write down the reverse reaction here for the first one, the sign here would change from positive to negative as a result. Also, very important, changing the coefficients of the half reactions will not change the value of the standard reduction potential. So even if I were to multiply any one of these equations by any numbers, these values will remain the same, all right? So that is a bit different from what you may be accustomed to when it comes to enthalpy, right? If you remember back in Chem 1, if you multiply a particular equation by, let's say, 2, then the corresponding enthalpy values would have to be multiplied by 2. That is not true for electropotential, all right? The electropotential does not change even if you were to multiply the entire equation by 100, right? The value of E0 will not change. Okay, so let's apply what we have just learned to solving this particular problem here, and I think we're going to stop here for this video. So this question says, what is the standard EMF of an electrochemical cell made up of a cadmium electrode in a 1.0 M cadmium nitrate solution and a chromium electrode in a 1.0 M chromium nitrate solution, all right? So basically what we'd have to do is look up the values in the table for the cadmium reduction, right? As you can see here, this is the standard EMF value. And for the chromium reduction, and that reduction potential is given here as well, all right? So basically you're hooking up this half cell to this half cell, and the question is asking for the standard EMF of the resulting cell made up of those two half cells, right? Now, the first question you have to ask yourself is which of these two standard EMF values is higher? And the answer, of course, obviously, is the first one, right? Minus 0.40 volts is higher than minus 0.74 volts. So what that means is that this reaction is more likely to occur as written, which means that for the second half equation, the reverse reaction is going to take place, right? So since the first one is of a higher value, that will remain as it is. That is more likely to occur, and we need to turn this one around. So if we turn this one around, then what's going to happen is you're going to end up with this, right? So this would be the reduction equation in one half cell, and the oxidation will take place in the other half cell, and this is the equation for the oxidation. And as a result of this equation being turned around to get this one, the sign of the EMF value will be converted from positive to negative. So this is the oxidation. The reduction would be this, which would be repeated down here. And then you add these two. And, well, before you add them, of course, you have to make sure that the number of electrons are the same for the loss and gain right here. So that means you multiply this equation here, in this case, by 2. You multiply this equation here by 3. And then the final equation will be what you get here. Now, the EMF value will be the result of adding these two. Now remember, these numbers are not affected by multiplying these equations by their respective numbers right here. So all you have to do to get the net EMF of this overall equation would be simply adding 0.74 to minus 0.40, and the answer turns out to be 0.34 volts. And that's basically it. That's basically how you would solve this particular problem, all right? So another way of looking at it is basically using this equation right here. The EMF of the cell will be equal to the standard EMF of the cathode minus that of the anode. So basically you just put the numbers in. The cathode EMF would be minus 0.40 volts minus the anode EMF, which is minus 0.74 volts, right? And that's it. You put the numbers in, and that's how you get it. And you're going to get the same result, right? I prefer to go this way, however, because this shows you basically step by step how everything will take place, how the anode reaction will take place, how the cathode reaction will take place, and the net equation, all right? But this is a shorthand way of doing the same thing. As long as you remember this equation right here, then all you have to do is plug the numbers in directly from the values that you got from the table, all right? Okay, I think I'm going to stop here for now. And then the next video, we'll be dealing with looking at the spontaneity of redox reactions. All right? Okay, until next time.